Hey there, students. Today I'm glad to announce the start of our brand new Calculus series that'll help you get through your calculus course and teach you important tricks for your university courses next year. Let's get started.
All right, students. So welcome to Ahead of the Curve's new Calculus series. So if you didn't hear it from the intro, the whole point of these series of videos, or at least the goal of these videos, is to educate grade 12 students that are currently in a high school calculus course such that when they attend universities next year, they'll be more than set up for their first year calculus course. So before we start tackling calculus itself, I think it's important that we understand the concept of what a limit is. So what is a limit? Well, all a limit is, it's just a value that a function approaches at a certain x value. So I'm going to write this down here. What a limit is, what is a limit? A limit is the value of y. And just to reiterate, if we were to look at these graphs here, the horizontal axis is the x-axis, the vertical axis is the y-axis. So basically, it is, again, the value of y that a function approaches at a given x value. So whenever they're asking you in class to evaluate the limit, what they're asking for is a value of y for a certain value of x. So now let's learn how to take an actual limit and how to represent the notation for these limits. So let's look at this first graph on the left here. So whenever we're evaluating limits from a graph, we first need to understand there are two types of limits that we can take. So I'm just going to erase this here. You can always write it down or pause the video if you need to. So to take a limit of a graph, I want to see what y value the function is approaching from both the left side of the x value and the right side of the x value. So what I want to figure out here is, what is the limit of this function as x approaches this value a right here? So the best thing to do at first is to take the x value in question. And what I like doing at first, you don't need to do this every single time, of course, but until you get comfortable with it, what I like doing is, whenever you're trying to evaluate the limit of a function graphically, I like to put an imaginary an imaginary dotted vertical line through that x value. And the reason why I'm doing this is it might be a lot easier for some people to see visually what part of the function is to the left of my x value and what part of the function is to the right of my x value. So by cutting this line in half, I can clearly see that everything here is to the left of my x value and everything here is to the right of my x value. So what I'm going to first do is I'm going to find what we like to call the left-hand limit. And simply put, the left-hand, the limit is y value that a function approaches as you approach the x value from the left. So the easiest way to do that is to simply use your finger or use your pencil. So because I've drawn this dotted line here, I know that this part of the function is to the left of my x value. So all I'm going to do is just, with my pen or with my finger, I'm just going to take this left piece of that x value and follow it along until I hit the x value itself. So following along here, all I'm really doing right now is I'm kind of focusing just on the function and the x-axis. I'm not even really looking at the y-axis right now. I'm kind of just following the function along with my pen or with my hand until I hit A. Boom, I've done that right here. Now what I'm going to do is I'm going to look at the y-axis and I'm going to see, oh, as I approach A from the left-hand side, the function's approaching B. So it looks like the limit of the function as x approaches A is just equal to B. Now we need a way to simplify, now we need a way to actually represent that with a specific notation. So here is the limit notation right here. So what we write down is we always start with lim, followed by the name of the function, which in this case, I've called it f of x. And then on the bottom of the lim f of x, we're going to write down what value x is approaching. So x is approaching, that's what the arrow's for, the value a. But to signify that it's a left-hand limit, what I'm going to do is I'm going to put a little minus sign right here. So this is representing here that I'm approaching a from the left. Whenever you see a minus sign kind of in the top right corner of your limit value, that means approaching it from the left. And I can clearly see that as I approach a from the left, again, following my pen along, I'm hitting b. That's the left-hand limit. All right, so pause and write stuff down if you have to. I'm going to erase some stuff. All right. So I'm just going to write that down. I'm just going to write down what we got over here. So I know that the lim of f of x as x approached a from the left was equal to b. Now we're going to find the right-hand limit. And very similarly to the left-hand, the right-hand limit is the value of y that a function approaches as we approach an x value from the right. So over here, to the right of this dotted line that I drew, clearly I can see this is the piece of the function that's to the right of a. So don't mind this arrow here. These arrows sometimes encourage students to think they can only follow graphs that way, or they can only follow graphs that way. The arrows aren't representing ways that you can move your pencil or look at things. The arrows are just representing that the function goes on forever and ever and ever in those directions there. But it has nothing to do with the fact that I can't follow a graph back this way from the right side, or I can't follow a graph back this way from the left side. These arrows are not telling you which way you're allowed to follow a graph. They just tell you again that the graph keeps on going. So I'm going to take this right piece and I'm just going to follow along with my pencil until I hit A. And then boom, again, the Y value that's hit is B. So very similarly to how I set up the notation for the left-hand limit of this function, I can do a very similar thing for the right-hand limit as well. So the limit of this function f of x as x approaches a from the right, and if I put a minus sign to signify approaching from the left, should make some intuitive sense that putting a plus sign will be approaching an x value from the right. So again, a right-hand limit, to represent that, it's x approaches some value, and you put the plus sign to signify that it's from the right. And as we included again, if I just follow the graph from the right-hand side till I hit A, the y value that's being hit is B. So now again, I'm going to erase some stuff. So in this case, it looks like the left-hand limit of the graph was equal to B, and the right-hand limit of the graph was also equal to B. So now we need to talk about if a limit exists or not. So for the limit of a function to exist at a certain x value, it must approach the same y value from both sides of that x value. So basically, we can conclude that because the the limit of this function as x approaches a is b, and because the right-hand limit of this function as x approaches a is also b, I can say that the overall limit, in which I don't put a plus or a minus sign down on my x value, would also just be b. So to conclude, a limit only exists if it approaches the same y value from either side of the function. And that's a very important concept to understand. Limits only exist if the same value of y is approached from both sides of that x value itself. All right. So clearly we can see that the limit does exist here, that the limit here as x approaches a is equal to b, because again, from the left side, we hit b, and from the right side, we hit b. Now let's look at this second graph here for this function g of x and see if we get the same thing. All right, we're going to erase all this stuff here. All righty. So let's do the same thing to this graph. I'm trying to see what's going on at the x value of a. So again, I'm just going to draw a little vertical dotted line through a so I can more clearly see the left-hand and right-hand side of this function here. Because unlike this function here, which is called a continuous function, and I'm going to get into that stuff more in a later episode of this series, this function here is what I call a piecewise function. The piecewise function simply because it's in pieces. At certain x values, it kind of looks like the function changes into something completely different. So from the left side of a, we got this little shape here, then all of a sudden, we have a different piece. And in situations like these, the chance of a limit not existing is going to increase, and we'll see what I mean by that in a second. So let's just simply first figure out what the left-hand limit and right-hand limit are. So again, this function is now called g of x. So I'm going to say the limit of g of x as x approaches a from the left is equal to, and then I'm going to write down the right-hand limit as well. I'm just going to kind of set these things up. I think it's usually good to set things up like this before you even start answering the question in the first place. And then, of course, I care about the overall limit at that x value for g of x. All right. So to the left of this dotted line is this piece here. I'm going to follow that piece all the way to a. Again, over here is a. I hit b. And then if I look from the right, so clearly the right of this dotted line is this piece here. I'm going to follow it from the right all the way to point A. I hit C. So as we can see here, the left hand, the limit is B, but the right hand limit is C. And just one more thing to clear up, guys, the left hand, the limit doesn't mean to go left, it means to approach from the left. So left hand limit is actually you going to the right from the left, and vice versa goes for the right hand limit. Right hand limit does not mean go to the right, it means come from the right. So we're going from the right and we're moving our pen left to hit that limit. Either way, I see that the left hand guy is B and the right hand limit is C. These guys are not equal to each other. So because the left hand and right hand limit are not equal to each other, we say that the limit of g of x as x approaches a does not exist. So again, a limit only exists if the left hand and right hand converge to the same value. All right, that's the basics behind how to find the limit value graphically. On the next page here, I have a little example of a more complicated function that I just want to go through before this session is over. So what I have here is a really complicated, annoying looking piecewise function. And I've picked a whole bunch of x values in which I want to evaluate what the limits are. So going from left to right, it looks like the areas of interest are x equals -4, x equals -1, x equals 2, and x equals 3. Just note here that this vertical line I drew here is not that vertical line I drew to kind of separate the left hand and right side of the function. This is an actual vertical asymptote. Alrighty, so let's evaluate what the limits are at all 4 of these x values. So looking at x equals -4. If I approach from the left side, which is this little piece here, I hit 1. I also encourage you guys to pause the video and try to answer these all yourself, then resume it later once you're done to see if we get the same stuff. I think this is a very good opportunity for you guys to test your skills. So as I approach -4 from the left, I hit 1. -4 to the right, that would be this piece here. As I approach -4 from the right, I hit -2. So it looks like here the left hand and right hand limit are not the same. which concludes that the limit overall as x equals -4 does not exist at all. And then finally, I think it's good that we can recognize what the value of y is at that x value as well. So I don't know what the value of f of a -4 is. And again, I'm just going to make sure this guy is going to be called f of x. Anyone is confused. So for f of a -4, we have an opportunity, or we have a choice, sorry, to pick from either this value here or this value here. This value I can see is a solid point, while this value here is a hole. Functions technically don't exist at the holes. So if I wanted to know what the value of y was as at x equals -4, I would definitely pick the solid point over the hole. So f of -4 is equal to 1. So let's keep going here. Now we're going to focus on x equals -1. So as I approach x equals -1 from the left, which is this piece here, so kind of note that as you're sweeping from left to right, it kind of looks like the right side piece of a previous x value might be the left side piece of another x value along the way. So it looks like the right hand side of -4 is also the left hand side of a -1. You can kind of continue this pattern as you sweep from left to right across the domain of x. So if I follow this piece to the left of -1 all the way up to -1, I'm going to notice that I don't actually hit it. I'm kind of stuck at this asymptote, and my values of y keep going up and up and up. So I can say that the limit of the function as x approaches -1 from the left is positive infinity. On the flip side, if I approach -1 from the right, which is this piece here, it's going all the way down, and that would be negative infinity. So because the left and right piece aren't matching up, the limit does not exist. And in terms of what the value of y is at this x value, there is no value of y at this x value at all. All I have is this vertical asymptote, and this function actually never hits the value of a -1 from either side. So here, f of a -1 also does not exist. All right, moving on. So now the next point of interest is x equals 2. So what I'm going to do is, following 2 from the left, looks like I'm on the axis, so 0. Following from the right, which is this piece here, I'm also hitting 0. So since the left hand and right hand side are both hitting 0, that will be the value of the overall limit as well. However, for the point itself, I don't see any solid point around x equals 2. So I have no choice to say that f of 2 does not exist. And then finally, when x equals 3, we can do the same thing. So the left side of 3, I'm approaching 2. The right side of 3, I'm approaching 2. So the overall limit as x approaches 3 is going to be 2. Because what's important to note here is the limit can still exist if there's a hole in place, because we're still approaching 2 from both sides. We don't need to actually hit it, we just need to approach it. So I want you to think that approaching something and hitting something isn't necessarily the same thing. I can still approach from both sides and hit myself a limit value. However, for f of 3 itself, the hole does not count as an actual point. However, I do see a point up here when x is equal to 3, and that is actually y is equal to 3. So f of 3 is actually 3. So it's possible for the limit value of a function and its actual y value to not be the same thing. And what we're going to do is, when you guys see me next time for this series, we're going to talk about how these types of limit problems and these types of situations relate to the continuity of a function, which will be kind of like the part 2 of this lesson, which I hope you guys tune into as well. Well, there we have it. That's how we evaluate limits graphically. Next time, we're going to learn how to evaluate limits algebraically and talk about continuity as well. Take it easy, guys.
Well, there you have it, students. I hope you enjoyed your first calculus lesson. Keep an eye out on our Facebook page or YouTube channel to see when the next installment comes out. And remember, whether you're just struggling in school or want to stay ahead of the curve, we have many amazing options available. Book a session with us now. Take it easy, everyone.